There we go. Hello everyone and welcome to 3.5, where we're going to talk about implicit differentiation. And towards the end of this section we'll also talk a little bit about differentiating inverse trig functions. I'll show you how to do that using this process of implicit differentiation. And then I'll just give you the derivatives for the inverse trig functions that you guys can just sort of study. So some functions that we deal with, when I say some, I mean basically all the functions we've encountered up till now, except a few here or there, have been very explicit. What I mean by that is they've been giving us these functions explicitly in terms of x. So I say some functions can be defined I'll use the word explicitly in terms of an independent variable for us it's typically x for our independent variable. So we would say f of x is a function of x, or y is a function of x if you want to kind of take the cheaper way out. And an example of that would be saying that y is equal to the square root of x cubed plus 1. Again, in the other notation, you might be saying f of x is the square root of x cubed plus 1. Right? So we kind of have two ways of saying it. One of them is using the legitimate function notation. The other one is, if we're looking at a graph in terms of x and y, we might just shorthand it to y. But y is explicitly given to you. It is explicitly told to you that your function is the square root of x cubed plus 1. So you know exactly what that function is. And you know how to differentiate it now using rules, such as chain rule and power rule and things like that. But there are some things that we look at in math that are not given to us explicitly, but they are implied. So other functions can only be defined what is known as implicitly by a relation. And an example of that would be something like x squared plus y squared is equal to 4. So if we would go to try and graph this, it's just a circle with a radius of 2. And we've all seen this before when we graphed our circles, right? It looks like x squared plus y squared is r squared. R squared is 4, so the radius r is just 2. So it's just going to be a circle with radius 2. Now, it's not a function because it doesn't pass the vertical line test. And what I mean by that is, if I were to take this and try and solve explicitly for y, I would run into something of the form y is plus or minus the square root of 4 minus x squared, where this plus or minus, to make it stick out a little better, is really what's hurting us. We can't write this as a function y equals this explicitly, because y is both the positive version of the square root and the negative version of the square root. So we can't be explicit. When I say to differentiate y, which one do you do? Do you do one? Do you do the other? Do you do both? Well, you can't write both as one derivative, so one derivative can't mean two separate things, one positive, one negative. So I can't explicitly write this as a function in terms of the independent variable x using just y. I'm forced to define the upper half and the lower half separately in terms of one gets the positive version, one gets all the negative version stuff. But that doesn't mean we can't differentiate something like this. Right? Even if we have something like this, we can still differentiate it we can still talk about rate of change anywhere I am on that given circle. So we want to be able to relay those concepts over to some more types of equations like this where we can't explicitly solve for y. Now, if it's ever a situation where you can explicitly solve for y, great, right? We have all the tools. But if it's a situation like this where we cannot explicitly come up with a function, just y equals, then we have to use what's known as implicit differentiation. And it is not a terrible task. It is simply just an extension of that chain rule that we've encountered. You're still differentiating a function, y, but you just don't know what y is explicitly. But that doesn't stop you from writing y prime, which is the derivative of y. You just don't have an explicit y prime sitting in front of you, unless you get lucky. So here I'm going to say how to differentiate explicitly versus implicitly. And what I'd like to do is I'd like to start out with something that we can differentiate explicitly. Let's say we start off with something like x times sine of x is equal to 1. So here's an equation, right? It's just a relation. And one thing that we can do to differentiate something like this is we can do it very explicitly. I know I'm dealing with x, and I know I'm multiplying by sine of x. X is my independent variable. The right-hand side is just equal to 1. So I can do this differentiation explicitly, which we haven't really done this really with just in terms of an equation just yet. But when we do differentiate, if we look at the left-hand side and we know it equals the right-hand side, then when we differentiate the left-hand side and differentiate the right-hand side, we keep the equality. If these are two unique functions and they have equality, then their unique derivatives maintain that equality. So this means that I'm going to differentiate the left-hand side, which means that I have to use product rule. It is the product of two functions. So it is the derivative of the first times the second plus the first times the derivative of the second. And then I also differentiate the right-hand side, but I'm differentiating 1, so I'm just getting the 0 to pop up on the right-hand side. So now I can clean this up. This is sine of x plus x cosine x, which is equal to 0. So I did that very explicitly, just differentiating with respect to x on the left-hand side. On the right-hand side, there is no x to differentiate, so it just becomes 0. So that is when I differentiate explicitly. But what if we look at x times y equals 1? Now when I look at this, I've replaced sine of x with the variable y. So I don't know what y is. Y could be a log function. Y could be an exponential function. Y could be a polynomial. In this case, I've already revealed the secret, and I've showed you that there is another function being multiplied by the variable x. There is an entire function being multiplied. But this is how I go through the process. If you don't get to see behind the curtain, and this is what's given to you, implicit, then you never knew that that was a sine function. And in fact, I can completely change this and make you do it again, and then change it to an exponential function and make you do it again. Change it to a polynomial, make you do it again. Change it to a different polynomial, make you do it again. Notice it would be different every time, but the process would be the same. You would get the first times the derivative of the first function times the second plus the first function times the derivative of the second function. But you wouldn't be able to identify the derivative of the second function if you didn't originally know the first function. Aha, that's the problem that happens here with implicit differentiation. I still use a product rule because it is the product of two functions. Here's the derivative of the first times the original second, plus here's the original first times the derivative of the second. Well, I don't know what y is, so I'm just going to have to write y prime, which is the derivative of y. And the right-hand side I differentiated is still 0. Again, to clean it up, I just have y plus x times y prime is equal to 0. Now again, if this is my function y, and I want to know what the derivative of y is, well, here it is right here. The derivative of just sine of x is just cosine of x. So if I really wanted to isolate the derivative of that red, I would have to do a little bit of algebra. Which means I would get x times cosine of x is equal to negative sine of x. But I want to isolate the derivative of just the red sine of x, which means I'm going to have to divide by x on both sides. Which means I will get cosine of x is equal to negative sine x over x. Now this was my original function y. Notice it's being negated, and then I divide by x. And what does it do? It produces y prime. If y is sine of x, then y prime is cosine of x. I can do the same thing over here if I subtract y, and then I get x times y prime is negative y. I can divide by x, so that I get y prime, my derivative, is negative the original function y divided by x. Whatever that original function was, there it is. It's being negated and divided by x. So here I got to explicitly see my function, and I can explicitly isolate my derivative of that function y. But if I cover this up, you don't know what it is, but you do the exact same process to identify its derivative. Only problem being, you never knew what it was, so you don't know what the derivative is explicitly, but you do know implicitly it has to have this form. So when you differentiate implicitly, you don't get to ever see the function. When you differentiate explicitly, the function is always there, hence you can just find its derivative and write it explicitly. So you can see how this will allow us to handle a lot more types of relations, like the equation of a circle or an ellipse or something like that. We cannot explicitly write it as a function, so we have to differentiate implicitly. So this one I could have done either way. Like I said, I pulled back the curtain to show you what the function was first, and then what the process looked like if you didn't know that function going into it. Well, now let's see what it looks like when you're never allowed to see that original function. Now we're going to close the curtain and say, we don't know what the function is back there, but we're still going to differentiate it without ever even looking at it. Right? So we're going to be able to differentiate things without ever even have to really knowing what the function is. So I'm going to go back to that equation of the circle with radius 2. I'm going to say let x squared plus y squared equal 4. That is the circle with radius 2. And I'm going to say find y prime using implicit differentiation. So again, we have a variable x, and then we have y, which is a function of x, but we can't cook up one explicit function. It's not going to pass the vertical line test. So we have to do this implicitly. So given the relation x squared plus y squared equals 4, and again, I say relation, It can be a relation because x is related to y, but we want to avoid calling it a function, right? A circle is not a function of x because it doesn't pass the vertical line test, but it is a relation. We can relate x to y. We just might get like separate y outputs for the same x input, and that breaks the definition of a function. So we do have a relation. I'm going to differentiate implicitly, meaning on the left-hand side, I'm going to differentiate with respect to x. Well, this is just x squared, and I know how to differentiate x squared using the power rule, 2x to the first power. Plus, I'm differentiating term by term, so that's why I differentiate this, plus now I differentiate this. Okay, y is a function. That means there's a function inside this square function. That means I need chain rule. I have a function inside of a square function. So what I do is I go back to chain rule, I differentiate the outer function, which is 2y to the first. I just rewrite the inner function. Right? So I bring the 2 down as a multiple. Now it's to the first power because I subtract 1 from the power, and I simply rewrite my inner function, but I don't know explicitly what that is, so I just rewrite y because that's all I know it is y. But then chain rule says you multiply by the derivative of the inner function. Well, my inner function is y, so I have to multiply by the derivative of y, but I don't know explicitly what that function is in terms of x, so I can't write it out in terms of x. But I do know that the derivative of y is y prime. That's the derivative of y. So this is my chain rule. That's done for the left-hand side. And then the right-hand side is just a constant. So if I differentiate it, I get 0. So again, we know how to differentiate x squared. We just do it. 2x to the first, done. Plus, because I can differentiate term by term, plus. I have an inner function y. This could be a log function. This could be an exponential function. This could be a sine function. Y could be anything. I don't know what y is exactly, but I do know it's the inner function, and the outer function is the square function. So chain rule says I take the 2 down as a multiple, rewrite the inner function, subtract 1 from the power. Now it's a first power. And then chain rule kicks in and says, don't forget to multiply by the derivative of the inside. Well, we want to find y prime, right? Our job is to isolate just y prime all by itself. So let's do that. Let's isolate y prime all by itself. Right now I'm just going to rewrite it so I have some space to work. First thing I'll do is I'll subtract 2x on both sides. I don't need that term because it doesn't have y prime in it. So I get 2y, y prime. These are all just being multiplied. 2 times y prime is equal to negative 2x. Again, y is not just a variable. Y is an entire function that you need x for. But I don't get to see it explicitly. So the only thing I can do is divide out by 2y on both sides. So I can get those to cancel and isolate y prime. That means I'm going to have y prime, which is my derivative, which is what I want, is negative x over y, or I'm simplifying 2 over 2. So now you can see that this is just a much more general strategy for attacking functions that could be like x squared plus cosine squared of x equals 4, or x squared plus e to the x squared equals 4, or x squared plus 5x to the 5th plus 2x minus 1 quantity squared equals 4. Right, you can see that this y function etc., etc., etc. You can see that this is a much more general strategy. If I can differentiate this and I know the pattern, then to get the derivative of any one of these, I simply have to take the ratio of negative x over y. If it happens to be cosine of x for y, I plug in. If it happens to be e to the x for y, I plug in e to the x. If it happens to be this polynomial, I plug in this polynomial. So you can see it's a much more general strategy. If I handed all three of these to you and said differentiate, 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 your intention probably right off the bat would be, okay, I have three problems to solve, this one, and this one. Whereas if you use implicit differentiation, you can identify the pattern in all three of these. It's x squared plus some function of x squared equals 4. You can identify that pattern and say, I'm just going to use implicit differentiation. There's y squared, there's y squared, there's y squared. And you've reduced having to solve three problems down into having to solve just one problem. And then you simply copy, paste wherever you need to put your explicit function. So you can see that is a very, very powerful tool. Even though we have less information, by less information, I mean we don't have the explicit function of x, it doesn't stop us from doing the calculus. And again, the reasoning for that is we have chain rule now. Once we have chain rule, we can differentiate anything. I say anything, but you know, I mean a function that has a derivative. Let's take a look at, what was I going to see here? See if we can find the derivative. I'll steal one of these even numbers here. Find dy dx by implicit differentiation. And obviously, if you see them say, you know, use implicit differentiation, it's probably a big red flag. That means you can't do it explicitly. That's probably the only way to do it. So let's take x cubed minus x y squared plus y cubed is equal to 1. All right, so this will be the relation that they give you. And again, we don't want to call it a function. We can't solve for y, so you know y isn't a function of x, especially with the mixture of cubes and square powers in there. But that doesn't stop us from finding a derivative for y implicitly. So again, I'm going to differentiate the left-hand side, and then I'm going to differentiate the right-hand side, and we'll see what we get. So I know how to differentiate x cubed. It's just 3x squared. I move on to my next term. Aha, this term has a product of two functions, which means I need to use the product rule on those two functions. Now, do be careful because you are subtracting the product of two functions, meaning you are subtracting the product rule. The product rule has a plus in it. That minus is going to distribute across that addition. So do be very careful. If you look at these two functions as x and y squared, you're going to differentiate them as the derivative of the first times the original second plus the original first times the derivative of the second. But this needs chain rule because it is a function inside of a square function, so I multiply by y prime. There's chain rule. There's product rule. Notice the minus has to apply to the entire product rule. Moving on to the next term. Well, that's just y cubed. It's a function inside a cube function. So I differentiate the outer function, which means the 3 comes down as a multiple, and I subtract 1 from the power. Now I go for the inner function because, again, this is chain rule. I'm differentiating a function inside of a function. That's a composition of functions. That always needs chain rule. Right-hand side is easy. A lot of the problems in the textbook, and even some of my problems on the study, or I say most of my problems on the study guide, there's probably just a constant lingering over there. I'll do one where it's not just a constant over there so you guys can see. All right, well, let's clean this up because our goal is to find dy dx. Again, we want the derivative. That's y prime, just in a different notation. 3x squared minus, I'm going to have y squared, and then I'm going to have minus, I'm going to just put the multiple out front of 2xy prime. However, this is just plus 3y squared y prime. So let's clean it up. We just want y prime all by itself. This term has y prime, this term has y prime, this doesn't, this doesn't. So let's go ahead and shift these over, get them on the other side. Cancel, cancel. Let's add y squared so it pops up on the other side. This means we have negative 2xy y prime plus 3y squared y prime is equal to negative 3x squared plus y squared. Doesn't matter which order you write them in over there. Just make sure you keep the negative with the negative and the positive with the positive, etc. Now we have a common y prime and a y prime. So I'm going to factor it out because it truly is in common with both of these terms, negative 2xy plus 3y squared. Right-hand side didn't change. It is what it is. Now I can isolate y prime simply by dividing by this expression. Right? This is y prime times all of this. I factored it out of both terms. Now I can divide out and simply say that y prime, which for us is dy dx. We can even write it if we really want to. Must be exactly negative 3x squared plus y squared divided by negative 2xy plus 3y squared. So there is our derivative. Now don't go canceling stuff out, right? We don't have a multiple of y squared that we can cancel out. We just have a term of it. Here's another term of it. Addition does not cancel with division. So again, algebra, very important. Right, if you do something silly algebra-wise there, then all that calculus was for naught. And again, that dy dx notation, that means the exact same thing as y prime. You can use that notation throughout the problem if you'd like to. I'll give you an example of that. Find dy dx. Or, and of course implicitly, e to the y sine of x equals 1 plus xy. Like I said, I want to do one where it's not just a constant on one side. So let's take a look. Left-hand side, right-hand side. There's definitely a product of two things on the left-hand side. And then there's 1 plus, well, there's another product of two things over there, x and y. And again, I don't know what the function y is explicitly, so of course we're going to have to use implicit differentiation. So this time I'm going to stick to this dy dx notation and show you you can use it throughout the problem. And you'll see why we usually like to shorthand with the y prime. It just looks a little neater, easier to follow. So let's look at the left-hand side. It is a product, so I do need a product rule. It is the derivative of the first. Well, if I differentiate e to the y, I need chain rule because this is an exponential function composed with an inner function of who knows what. So since it's not e to the x, whose derivative is e to the x, I'm not quite finished differentiating with respect to x because I've only touched y. So chain rule says I have to multiply by the derivative of whatever that function is up there, but I don't see it explicitly, so I do it implicitly. There's the derivative of the first times the original second sine of x. Product rule gets the plus. Here's the original first function, e to the y, times the derivative of the second function. That one I can do explicitly. It's cosine of x. So that is the derivative of the left-hand side using product rule, and I surely needed chain rule on the first one. Now I just differentiate the right-hand side. Derivative of 1 is 0, nothing to write. I have the product of x and y, so I do have to differentiate that. There's the derivative of the first times the original second. Product gets a plus. There's the original first times the derivative of y, which is y prime. All right, if I differentiate y, I get y prime. And I told you I was going to use the dy dx notation. So here, where you see your y primes, you can see where the dy dx notation is going to get a little bit cumbersome. And maybe I'll highlight it by doing it in blue. You're going to have dy dx. All right, see how that could be a little bit more involved rather than just writing y prime. But, I mean, still doable. Okay, so when we write it out like this, notice now we have a dy dx, aka y prime, on both sides. Whereas in the last problem we had, two y primes that we had separated, amongst addition. We had to factor it out and isolate it. We didn't have to worry about it also being on the right-hand side. Now it's on both sides, so our job is going to be to get them on the same side so I can do that factoring out process. So I'll show you what I mean. I'm going to subtract, and I'm going to pick to put it on the left just because that's maybe a little more natural. I'm going to subtract this whole term of x dy dx and bring it so it pops up on the left-hand side. And this does not have dy dx, so I'm going to subtract e to the y cosine x so that it pops up on the right-hand side. All right, so notice I want dy dx equals everything else, so I'm getting my dy dx on the left-hand side set it up so I can isolate it. So it's just like solving, a linear equation or something like that. You want all your x's on one side, all your numbers on the other. Well, now we're not dealing with just numbers and x's, we're dealing with functions. Right? So I want my derivative, which is a function, all those on one side so I can isolate. Now I'll rewrite it. E to the y, dy dx, minus x. I forgot my sign of x in there. E to the y, dy dx sine x, minus x, dy dx. This is gone because it's canceled. On the right-hand side, I still have this one y here, so I'm going to write y. These are canceled. I have minus e to the y cosine x. So again, at this stage, you should say, all right, this is all my dy dx stuff on the left. Yes, it is. I got two terms separated by subtraction. Do I have any leftover dy dx's over here that I need? No, I don't. That's just x's and y's. So let's go ahead and factor out dy dx. Because it's in this term, e to the y sine x, and it's in this minus x term here, which leaves me with the same thing on the right-hand side. I never touch it. But don't be lazy and not rewrite it. If you don't write the right-hand side and just write the left-hand side and then go on to the next step, I'm going to put a big question mark there and go, what? That doesn't make sense. You went from an equation to an expression, and even if you bring it into the picture in the end, right, you just left out half the story. And I'm going to circle that big empty space and go, where's the rest of the story? Right, don't be lazy, write it down. But now I have to divide out by e to the y sine x minus x on both sides, just because I don't have that space there. Picture that division, it cancels out. And then I have on the right-hand side y minus e to the y cosine x divided by e to the y sine x minus x. And that is the derivative of y. This is the derivative of that function that I have no idea what that function is. I never ever knew what y was. It's some function that's defined by x. I never knew what it was. It could have been another exponential function here and here. It could have been tangent of x here and here. I don't know what it is, but notice I know its derivative. It does still involve x's and y's. So I still don't know exactly what this is because I never knew exactly what y was. But the nice thing is, if I have to evaluate this thing, say, at a specific ordered pair, like x is 1 and y is 7, then I know where to plug in my 1s for x and my 7s for y's. So if given a point or an ordered pair like that, you can still plug it in and evaluate the derivative. And what does that tell you? Well, it tells you the rate of change at that point. So even though you have no idea what the function y is, you can still tell me the rate of change of that function. Isn't that kind of weird? You have no idea what the function is, but you know how fast it's increasing. That's powerful stuff. So I never even told you what the function was, but you can tell me what its rate of change is. That's some really neat stuff there. Let me see. Let me steal one with an equation of a tangent line. It's been a minute since we've done one of those. Give myself some space. So again, you don't know the function, but you can still do some analysis and see what that the rate of change of that function is at a given point. That's really weird. That's like me saying, hey, there's an animal in my backyard. Tell me how fast it goes. And you'll say, oh, well, what's the animal? And I say, I'm not going to tell you, but tell me how fast that animal can run. And you're going to say, 8 miles an hour. And I'm going to say, good job. And then I'm going to ask you what the animal was, and you're going to go, I don't know. But you know how fast it moves. That says a lot, right? That is really powerful stuff that you can analyze something and not even know it explicitly. So let's look at one where we look at the equation for the tangent line. So we're going to use implicit differentiation to find an equation of a tangent line to the curve at the given point. And we'll look at, this will be x squared plus 2xy plus 4y squared equals 12 at the points 2, 1. Now, if you really do enough digging, if you really want to, and you dig deep enough back into an old pre-calculus book, you could tell me what this equation actually represents. It's a conic section. In fact, it's an ellipse. So this is the more what they call like the general format, where they give you everything laid out in terms of a polynomial, in order to really get it to look like the way you're used to looking at equations for parabolas, ellipses, hyperbola, stuff like that. You'd have to do some completing the square and all that weird junk. We don't need to do that. Right? We're going to use implicit differentiation. We want to find an equation of a tangent line. Immediately, that should tell us that in order to form an equation for a line, we're going to need a slope and we're going to need a point. Well, lucky for us, we have the point. So we're already halfway there. I say halfway there. We got a lot more work to do, though. How do I get that slope at that point? Well, I need to find the derivative and then plug in this x value and this y value. Right, you need the derivative to get that slope of the tangent line. To get that rate of change at that point, you need the derivative. The only way to go about differentiating this, since you don't know what y is in terms of x explicitly, is by using implicit differentiation. So for implicit differentiation, this is x squared. I just differentiate it straightforward. That's 2x. Plus, now I have the product of two functions. I'm going to look at 2x as the first function and y as the second function. I'm going to include that 2 as part of the first function. So when I differentiate the first function 2x, I get 2 as a result. And then I'm going to multiply by my second function y. Product rule gets a plus. I don't have to worry about a negative out front here. Positive, positive, everything's good. But I do now have to keep the first function 2x and differentiate y. That spits out y prime. Plus, now I have to do this term. Well, this is 4y squared. There's a function inside a square function, so the power comes down. 4 times 2 is 8y to the, I subtract 1 from this power of 2 to get it to a linear power. But I just differentiated y, the inner function. Chain rule says I must multiply by the derivative of that inner function y, which is y prime. Right-hand side, well, it was a constant 12, so now it's just 0. So it looks pretty messy. We want y prime because y prime will tell us the rate of change once I plug those numbers in that ordered pair. So I'm just going to clean it up a little bit first before I go adding and subtracting a whole bunch of stuff. And by clean it up, I really just mean get those parentheses out of the way. I don't want to see them. Get rid of this 2x. Get rid of this 2y. That isolates anything with y prime on one side. Once those are isolated, we can go ahead and factor. So there's y prime, there's y prime. Let's go ahead and factor out y prime. I'll get 2x plus 8y. Still get negative 2x minus 2y on the right-hand side. We'll go ahead and divide out by 2x plus 8y on both sides. And this will reveal that my derivative, y prime, is going to be negative 2. I'm going to factor that out. When I factor the negative 2 out, I get negative 2 times the quantity x plus y, because I'm also factoring out the negative. And then I'm going to write 2 times the quantity x plus 4y. Be careful because there's an 8 there. So if I factor out the common 2 after I divide, let me show you. That's what I'm doing. That's what I'm doing. And cancel that with that. There's y prime. And then I'm just simply isolating out, I'm factoring out 2 from the denominator and negative 2 from the numerator, so that then I can just make one last final cleanup by making my calculations a little smaller. So here we go. This is y prime. It is negative quantity x plus y over x plus 4y. Now what I want to do with that is plug in this ordered pair 2, 1. That's my point. If I plug that point into my derivative, it will tell me the rate of change at 2, 1. Once I have that rate of change, I have my slope. So I'm going to just kind of split this up here. We could fit it in so that we get our equation for our tangent line. It's not going to take too long. So here's y prime. I don't know if we've used this notation yet. I don't believe we have. When you see this vertical bar, this is the same thing as saying y prime evaluated at 2, 1 is going to be, wherever I see x, I put 2, because that's how ordered pairs work. The first one is always x. And wherever I see y in here, I put a 1. Again, that's how ordered pairs work. So I'm going to do minus 2 plus 1 quantity over 2 plus 4 times 1. So again, when you see this vertical bar notation, and we'll see that a lot more as we progress through the course, this means evaluated at, and then whatever that is right there is where you plug in. So that's a nice way of just writing it down. Rather than just randomly saying y prime is this in terms of x and y, which is 2's and 1's. You're saying, well, wait a minute, okay, I get what you're doing, you're plugging in 2 and 1, but y prime does not have 2 and 1. Y prime is more general. Y prime is always in terms of x and y. Y prime with this point plugged in is 2's and 1's, for sure. So that gives us negative 3 over 6, which is negative 1/2, which happens to be our slope. So now we know what our slope is, and we know what our point is. Thus, the equation for the tangent line is, and again, I'm just going to go back to that point slope form. Y minus, there's y1, is equal to m. We want the slope for our tangent line to match the rate of change, which is our derivative, evaluated at q1. So we've got negative 1/2 times x minus, there's x1, which is 2. And then just to make it look like an equation of a line y equals, we can play around with it and say that y is negative 1/2 x. This will be plus 1, but then I'll add another 1 to get plus 2. All right, so distribute this out, negative 1/2 x, negative 1/2 and negative 2 is positive 1, but then I do have to add 1 to both sides. So the positive 1 plus 1 is positive 2 on the end. So there's our equation for that tangent line. So the differentiating got a lot more involved, right? But again, implicit differentiation it's not too terrible. It really is just a more general extension of the chain rule. But you can see the process for finding the equation of the tangent line is always the same. Derivative, plug that point into the derivative. There's your slope, point, slope. Write it down. So the process doesn't change at all. The implicit technique is just something a little new. Let's see, got another one on deck here. Yeah, this one is find y double prime, that is the second derivative of x cubed minus y cubed equals 5. I don't know if it was a plus or a minus. Oh, it was a minus. Okay, so we're good. So we want to find the second derivative of x cubed minus y cubed equals 5. I'll show you how to do that using implicit differentiation. Obviously, we can find the first derivative, and then once we've got that, we can just differentiate it to get the second derivative. So it's just going to be, approximately twice the work. So first, we're going to find the first derivative using implicit differentiation. That is to say 3x squared minus 3y squared times y prime is equal to, right-hand side 0 because I just differentiated the number 5. So again, you're not seeing like an x prime here, right? If I were to look at this as my inner function x, then when I differentiate x, I just get 1. So chain rule is not going to contribute anything. That's why you're not seeing anything here. But y is a lot more involved. This could be a trigonometric function, which means when I differentiate a trig function in a power function, chain rule has to have me differentiate that inner function and multiply by that. So I don't know what this is. This could be 1. I don't know that. But I need it there as a placeholder so that if it is not something that is like multiplying by 1, I don't get in trouble. But you can see it's pretty quick from here to try and get y prime isolated. Negative 3y squared times y prime equals, if I subtract this over, negative 3x squared. Which means now I can divide out by negative 3y squared, which was that thing sitting out front of y prime. Cancel all that out in one big chunk. Isolated now is my first derivative, y prime, and it cleans up very nicely, negative 3 and negative 3 top and bottom. So I get x squared over y squared. Now, I'm not quite done yet because it wants the second derivative. And so far, I've only got the first derivative. So now I need to go for finding y double prime. So I just need to continue this process of implicit differentiation. This one's just going to happen to use a quotient rule now. There's nothing I can do with that ratio. Y squared stuck down in the denominator. So I'm just going to go for a quotient rule, which means I differentiate the left-hand side. Well, the derivative of y prime is y double prime. Right, now that you've got y prime isolated and you know exactly what it is, you can just differentiate it to get the second derivative. That's the actual really nice part about this. Here you did not have y isolated, so it was kind of a chore to get y prime isolated. Now you have y prime isolated thanks to all your hard work, so y double prime is right there. But now I have to differentiate the right-hand side to show that that is the second derivative. I do the derivative of the top, which is 2x. And I'm always differentiating with respect to x, so that's a nice and easy job. And then I multiply by the original bottom, that's y squared. Quotient rule always gets a minus. Now I do the original top, which is x squared. And I have to multiply that x squared by the derivative of the bottom. Aha, this is implicit because I don't know exactly what that function y is. Since it's a square function with another function y inside of it, the 2 comes down, I reduce the power by 1, and then chain rule says I have to multiply by y prime. Then quotient rule isn't quite done yet because I have to square that denominator function, so it's y squared squared. So it looks a little messy. Again, we don't want to leave things messy, so we'll just go ahead and clean it up. I'll get 2xy squared minus, there's 2x squared y prime. Y squared squared is y to the 4th. But now it's pretty sloppy because what I'm looking at is, I'm looking at x's and y's and y primes and y double primes. But the nice thing about this is, we know what y prime is. We know what y prime is. So I'm not going to leave that as y prime. I'm going to make it so that everything on the right-hand side is in terms of x's and y's only. They may have some funny powers acting on them, but I can look at this as 2xy squared minus 2x squared y. Y prime is x squared over y squared. And then the bottom is still y to the 4th. And I can do a little bit of reducing because there's a multiple of y, and then I'm dividing by y squared. So I do have to divide by y still. And then x squared and x squared is x to the 4th. So here's y double prime is equal to 2xy squared minus 2x to the 4th. I still have this extra division by y. And then on the bottom, I still have y to the 4th. Move this down a little bit so it lines up a little better. Well, now I've got this like complex fraction thing going on. So rather than leave it like this, I'm going to divide by y here and multiply by y, just to get a nice common denominator up top. Let me separate that. So that y double prime is going to be equal to 2xy cubed minus 2x to the 4th divided by y to the fifth. All right, so common denominator of y, but then I'm going to multiply by the reciprocal of y to the fourth, which is 1 over y to the fourth. So you can see that I'm dividing by y and then dividing by 4 more factors of y. So I'm dividing by 5 factors of y. You could actually factor out, I mean, this is perfectly fine as an answer from here, but some people may want to factor out 2x from the stuff up top and get y cubed minus x cubed. Don't know how much fancier or nicer that looks, but it is doable. You've still got 2xy cubed, and if you distribute, you still got 2x to the fourth, and after the subtraction. That's kind of up to you. But we're done with it, so we'll just say that's it. And as far as implicit differentiation goes, that's the technique, that's the strategy, that's what we're doing. And it's mostly stemming from chain rule. And just not being able to explicitly differentiate the way we've been doing it before, because we were being given too much information, right? Now they're giving us less information and asking us to do the exact same thing, the exact same work to the exact same quality, which is actually doable thanks to the chain rule. That's how strong chain rule is. And then last thing I want to do is work on a couple examples. Well, show you how the implicit differentiation can help us find derivatives of inverse trig functions, and then work on a couple examples there. So here are the derivative, or I should say derivatives, of inverse trig functions, meaning sine inverse, cosine inverse, tangent inverse, etc. Now, I'm not going to directly show you how to compute all 6. Once I show you one, you can pretty much just use that same technique to figure out the others. So let's say we're looking at the function sine inverse of x. I'll use the inverse notation rather than the arc sine notation. It'll be a little faster to write. What this means is that sine of y must equal x. So what's being said essentially is sine of some angle spits out some value. Right? What the sine inverse function does is it takes the inverse of that value and returns the angle. Right? Sine of an angle gives you a value. Sine inverse of a value returns the angle that you're looking for. But when you look at the sine function, or rather I should say when you look at the sine inverse function, x has to be between negative pi over 2 or positive pi over 2. Or I'm sorry, I should say for sine inverse of x, y has to be between negative pi over 2 and positive pi over 2. So we do have to worry about when we look at these functions and we look at the inverse trig functions, we are quite restricted when it comes down to looking at the range of what that inverse trig function can give us. So let's take this and look at this in terms of implicit differentiation. If I were to try and differentiate sine of y is equal to x, well, first of all, I have an outer function, sine, that I need to differentiate, and then I have to worry about differentiating the inner function using chain rule. So the derivative of sine of y is cosine of y, but then chain rule says I need to multiply by the derivative of y, which is y prime. The derivative of x I can do explicitly on the right-hand side, that's just 1. So if I isolate y prime, sorry, that was meant to be an arrow. If I isolate y prime by dividing by cosine of y, I get this for my derivative. But this is just y. When I look at cosine of y, oh, it's like, well, give myself some more space here. When I look at cosine of y, that is like me saying 1 minus sine squared of y under the radical. Why is that? Well, this is an important situation here. Because y is between negative pi over 2 and pi over 2, then I know that cosine of y is going to have to be this positive value. So I'm going to take the positive square root, and I'm going to look at this cosine of y in terms of y prime is equal to 1 over the square root of 1 minus sine squared of y. Now I'm squaring the whole sine of y, so really what it looks like is y prime is 1 over the square root of 1 minus sine of y quantity squared under the radical like that. So the sine function is being multiplied by the sine function. All right, so this goes back to just an old identity. Cosine of y squared plus sine y squared equals 1. You could subtract sine squared of y over. You can take the square root. But we're stuck taking the positive square root here, just simply because of our domains. Now this is sine of y, and this is exactly sine of y. So I can replace this, since I've got it rewritten in terms of what sine of y originally is, right? If sine inverse of x is y, sine of y is exactly x. So I'm going to rewrite this as exactly x and say that y prime is equal to 1 over the square root of 1 minus x squared. So here, the y prime is 1 over radical 1 minus x squared. Here's y, which is the sine inverse. Here's y prime, which can be rewritten as this 1 over square root 1 minus x squared. So you can see that when you differentiate that inverse trig function, you don't get another inverse trig function. It doesn't quite behave that, that same way. This is way too cumbersome to do every time. Right? If someone tells me to differentiate the sine inverse function, I do not use implicit differentiation. I just know that this is the derivative of the sine inverse function. And that's what we're going to do. There's only 6 inverse trig functions that we need to really worry about. So it's good to see it once, but you don't want to do this process and have to go through the whole explanation of, especially things like, you're looking at the sine inverse function, so you want to know what the range is. Well, the sine inverse function goes between negative pi over 2 and positive pi over 2. You have to take that information, transfer it over to here, because if you just look at cosine squared of y plus sine squared of y is equal to 1, then cosine squared of y is 1 minus sine squared of y. And if you really want to get cosine of y isolated, you would get a plus or a minus square root 1 minus sine squared of y until you hit this justification, and that justification comes from the definition of the inverse sine function. Then you're allowed to say it's just this one, not the positive and the negative, it's just the positive one. Then you have to rewrite this in terms of what sine of y actually is based on sine inverse of x equaling y. Like, why go through 10 steps when you can just look at sine inverse of y and know its derivative? Right? Just like when you look at sine of x, y equals sine of x, and you know its derivative is cosine of x. Right? You don't have to go through any crazy process to show that. You don't have to do the limit definition of a derivative to go through that. You don't have to go through any craziness. So that's going to be our goal. Let me put this over here. So first one's done. If y equals sine inverse of x, then y prime, the derivative of the sine inverse function, is 1 over the square root of 1 minus x squared. So there's our first one. We can do that same process again to show that if we're looking at cosine inverse of x for our function y, then y prime is going to be negative 1 over the square root 1 minus x squared. So you just have a little extra negative to deal with. Not too bad. If y is tangent inverse of x, then again, similar process, y prime is going to be 1 over 1 plus x squared. If y is equal to, let's go to cosecant inverse of x. The reciprocal functions you don't see as often. See a lot of these sine inverse, cosine inverse. I see a lot of tangent inverse in Calc 2. Calc 2 just seems to love that because it's actually a really nice function to deal with. Then we'll get negative 1 over x square root of 1 minus x squared. Oh, I'm sorry, I have to flip-flop the x squared minus 1. Reciprocal identities. There you go. That'll work out. If you look at secant inverse of x, then y prime is going to be, now we need positive 1 over x radical, and again, x squared minus 1. Be careful, sine and cosine, the way they're formatted versus, sine inverse, cosine inverse versus the cosecant inverse and the secant inverse functions. They have a little extra x variable down in the denominator, and they're also looking at x squared minus 1 instead of 1 minus x squared. So just a little change there. Like I said, the more popular ones are sine inverse, cosine inverse, and tangent inverse. But we do also have cosecant inverse, secant inverse, and of course, cotangent inverse. Y prime is negative 1 over 1 plus x squared. Not too bad from the tangent function, just has that extra negative in there. So these are all 6. And notice, again, you're looking at inverse trigonometric functions, but then it's going to pop out some sort of weird algebraic expression in terms of x. That's just based on the process. And then I'll just steal a couple problems out of the book to show you this is really not too bad. So let's take a look at find the first derivative of, and I'll just steal a couple and we'll work them out. Y equals tangent inverse of x squared. Aha, now that's not just tangent inverse of x, that's tangent inverse of x squared. There's another inner function plugged in there. So I have this inner function that I'm going to have to worry about. Now if I want to differentiate tangent inverse of something, y prime is going to be 1 over 1 plus x squared. But this is my argument in here, which is x squared. So that is the argument that I have to put in there, x squared. So I do have to be careful about using those chain rules still. To make sure I'm getting the proper derivative. So I'm differentiating the tangent inverse function. I would just get 1 over 1 plus x squared, but I have to rewrite the inside thanks to chain rule and then multiply by the derivative of the inside thanks to chain rule. Now I'm just simply multiplying by whatever that derivative of x squared is, which is 2x. So y prime is 1 over 1 plus, I'm sorry, I'm going to write 2x in the numerator, so it just takes up the same amount of space. And then, of course, x squared squared is x to the 4th. Now it's just one nice rational expression. So we still do have to watch out for chain rule. That is still a thing. And let's take a look at what we got there. Cosine of this one is y equals arc cosine of the square root of x. So if we're going to differentiate this, then what we want to do is say y prime is, when I look at this is cosine inverse, when I look at arc cosine, I need a negative 1 over 1 minus whatever this argument is, which in this case is not just x that I need to square. I need to square the square root of x. I really didn't give myself enough space there. There we go. So again, whatever is inside here goes inside here to get squared up. But now I just differentiated the composition of this cosine inverse function with the square root function. So I need chain rule to have me multiply that entire thing by the derivative of this. Again, square root of x is really x to the 1/2. So when I differentiate x to the 1/2, the 1/2 comes down, and I reduce the power by 1. So you can see what I'm doing. Whatever this is inside goes right here. If this was tangent inverse of smiley face, then I would have 1 over 1 plus smiley face squared. But I'd have to use chain rule because I don't know what the derivative of smiley face is, right? So same thing over here. Whatever this is in here goes right here and gets squared. But then chain rule says you also have to multiply by the derivative of whatever that inside was. So we can clean this up a little bit because the square root squared is just x. So I've got negative 1. And again, the negative's there because it's cosine inverse, not sine inverse. 1 minus x. This 1/2 x to the negative 1/2 really tells me that I have a square root in the denominator here. Rather than leave it broken up as two different expressions like this, multiplied, let's just go ahead and put negative 1 up top. And everything on the bottom that belongs on bottom 2 times the square root of x times the square root of 1 minus x. You could force those two together and do x minus x squared. I guess that's pretty much it for that problem. But if you really wanted to, since it's the product of two radicals, right, this radical times 2 times this radical, I could bring it under one radical and write it out like that if I wanted to. But there's not really nothing wrong with that. That one, maybe a little cleaning up would still be nice, but nothing wrong with that. Nothing wrong with that. Definitely nothing wrong with that. So yeah, that's about it. There's a couple good ones to practice in there, but not a whole lot. I would say out of the thing to concentrate on, obviously chain rule practice. Once you got your chain rule practice, definitely do some implicit differentiation because there's lots of equations out there that can't be defined, just by using an explicit function. But things like conic sections, you can still graph those. You can still have a relation between x and y. That's just a little more involved. Can't be explicit, but you can still differentiate and find rates of change and stuff like that. Inverse trig functions, I'll be the first guy that says not the most important thing in the world when it comes to differentiating. It really is just a bunch of know this, know this, know this, know this, know this. But when we get to the end of Calc 1 and we start integration, which is just basically going backwards, starting with the derivative and trying to recover this function, that's when they become really important. So, don't avoid them right now, but really when it comes to differentiating them, it's going to feel very just memorized, mechanical, not fun. But when it comes to integrating, integration is really an art form, and it is, like untying a knot. It's really like a little puzzle you need to solve. When it comes towards the end of the course with integration, you're going to really want to remember what those inverse trig functions are when you differentiate them, so that you can work them backwards to get back to the inverse trig function, right? Because if you come up with some weird algebraic expression, how is your brain supposed to know to work it back to the inverse trig function? Well, it's got to know how to work it forwards first in order to get it worked backwards. So you'll see these pop up again later in the course. And of course, Calc 2, you'll see them quite a bit, so you'll want to know them. So that's it for 3.5. Again, lots of chain rule being applied to the concept of implicit differentiation. Practice, practice, practice. And then, of course, the inverse trig functions also practice. But there's only 6 of them, so it's a limited amount of practice you can do with all 6. But keep throwing chain rule and stuff in there like that. And throw a polynomial in there, rework the problem, see how it changes things. So that's it. And then the next section, 3.6, we'll finally get that logarithmic function. So it's been a while, and we haven't even touched the logarithmic function as far as differentiating. So 3.6, we will finally make sure I definitely get, derivative of logarithmic functions will be the next section. So stay tuned.